So now we're going to get into what I think is one of the more interesting parts of these early Java classes, and that's sorting and searching through an array. And this is probably this is the understanding sorting and searching through arrays is a critical task in all programming languages, and how to do it efficiently and effectively is critical. So understanding these basic algorithms will really help you in your programming. You'll often need to determine whether or not array contains a particular value. So here's the pseudocode for an algorithm for conducting a sequential search for a particular value within an array, right? We have an index, and we're going to set it equal to 0. And while that index is less than the number of filled elements, and this is kind of a key thing, right? Filled, because we can have an array of 100, but only 50 of them might be filled. If the array at index I equals the search for value, then do something and stop the loop. Otherwise, increment I and check the next index, and check the next one, and check the next one. Go, over and over and over again until you find it. Or if you don't find it, then you should also return something that says, hey, I didn't find it. This is a common thing. So we're going to work through all these different algorithms in class, but you should try to implement them on your own to see if you can figure it out. So given this problem description, I want you to write a helper method named findStudent that searches for an ID value with an array of student IDs. The findStudent method should receive an ID parameter and return its index value of the ID's location within the student ID's array instance variable. And if the ID value isn't found, then return -1. So I would like you to try to do this on your own. If not, we're going to work through this in class, but it'll really help you to cement how it works. So just go ahead and see if you can figure out, given this problem description right here, try to implement this on your own. So here's the code that's going to be available to you on Canvas. It's the starter code for this thing. What I want you to do is I want you to update the findStudent function, the findIndex function or method with your own code. So do stuff, return 0. You're going to swap this out for some code that actually goes through. It's going to iterate through the array looking for the name that was passed in. Also, you're going to pass in the array. So I want you to try to update this code and have it work so that actually it prints out the correct response. Because right now, whatever you type in is just going to print 0. So if we run it, right, and I pull this over here, and I say, hey, I want you to find Corey. Position of Corey is 0. If I say Bob, right, it's going to return 0. If I say something that's not even in there, it's going to say 0, right? So it should return either the index or -1 if it's not found. So that, I want you to go ahead and pause the video now and see if you can figure out how to do that. And we're going to take a look at it in class, but that's your goal. Now, not only is searching an array important, but sorting an array is also important. And most programming languages have methods and utilities available to you to sort arrays and to sort your collection objects. So you don't necessarily are going to have to implement your own, but it's good to understand how that they work and the different trade-offs that you can have with the different arrays and the different sorting mechanisms behind them. So we're going to go ahead and take a look at those now. So sorting an array is a very common task, as I already said. And you use it to sort emails in your inbox, either by date or sender, or maybe use to sort songs by title or author, right? Or maybe we use it to sort student records in our class, right, by student ID. So we come across this stuff all the time as far as things that we want to use sorting for. So you could include a sorting method in every class that needs sorting functionality. For example, you could include a student sort method in a student class that sorts students by student ID. Or maybe you have a book sort method in a book class that sorts by ISBN number. Or maybe you've got a product sort method in a product class that sorts by product ID. But suppose that you want to make a generic sorting method that receives an array as a parameter, like student IDs, book ISBNs, or product IDs, and sorts it. How do we go about doing that? Well, to make the sorting method generic so that it can be used by multiple classes, we would put the sort method in a utility class, like such. And a utility class is a class with general purpose methods that other classes can easily use. And to make the methods easy to use, we use class methods as opposed to instance methods, right? So why would this be easy for other classes to use the sort method if the sort method is implemented as a class method? Well, think about that and think back to last semester. That's because we can call it without instantiating an object of type utility, right? We can just call it by the class name and then sort array, and we pass in the array. So let's do a quick recap of class versus instance methods. If you make the sort method an instance method, then you are required to instantiate the sort method's enclosing class prior to calling the sort method. For example, assuming the sort method's enclosing class is named sort, right? Then we would have to make a class object called s of type new sort, and then we could call s.sort student IDs. And s really isn't doing anything. We're not using it to store anything. We're just creating it just so we can use its methods. And that seems kind of silly. So using it as a class method, we can just call sort.sort and pass in the IDs, right? We don't actually have to create this new thing. We don't have to store it in memory and so on and so forth. So that's the difference between the two. Now, with that being said, there are many different sorting algorithms with different characteristics. We have things that are better computationally, right? As far as complexity, which things take the least amount of time to run on your computer? What types of sorting algorithms use the least amount of memory, right? Which sorting algorithms are stable, meaning is relative order maintained? So if item 1 comes before item 7, but they're already sorted by whatever way you're going to sort them, will they maintain their positions or will they get swapped? We'll take a look at that. And also recursion. Does the sorting method call itself? And we'll talk about recursion briefly, but we'll get more into it in the C++ class. So don't worry about it if we don't get to it this semester. So I think this is a really cool website that I found that really shows the difference between the different sorting algorithms. So you can try to run all these different sorting types, and here you have a random assortment, and you can watch it go through and sort the items using its algorithm, right? So there's that, or we can do a selection sort, and you can see how it operates differently. And you can see like insertion sort so far was a lot faster than, or selection sort, insertion was faster than selection. What about bubble sort? Let's take a look at bubble sort. How does it do in its thing? So it's pretty interesting. Here we have a few unique, here we have reverse, here we have nil. So you have different array, you have different ways that the data is already stored. So which algorithm you choose can have a big determination on which one, is better. So if we reset and do random, you can see them all running right here, right? So insertion sort was pretty quick, but we got some faster ones. Let's run it again. Which one's done the fastest? It looked like heap sort was done first and merge was pretty quick. What about if they're nearly sorted, right? Wow, selection sort is terrible. If they're nearly sorted, insertion is hella fast. right? But then there goes our selection sort again. Super slow. What about if they're reversed? Shell sort was done very fast. All these were done fast. And we're going to talk about the difference between all these different algorithms, right? What about a few unique? There you go. So as you can see, selection sort and bubble sort are pretty bad by themselves. But they're really simple to implement, right? So if you run them all, it's kind of fun. So heap sort and merge sort are really good. So is quick sort. And we'll get into merge sort maybe, but not quick and quick 3. But this is really interesting to look at, and you can also do problem size of 50, right? Wow. Okay. So what if we have a random array of 50 items? So let's run it. And you can see heap, shell, and merge, and all of these all finish at about the same time. And we'll get into why these ran that much faster. That's because these are all log n complexity times versus these, which are usually n squared. And we're going to talk about big O notation next.